rules of derivatives. We'll start with the constant rule. Rather than having to do the limit definition every single time, we're going to do the limit definition once and come up with a generic rule for the derivative of any constant. We'll call it c. So this implies that our function is c, and c is just some constant. So recall the limit definition. The limit as h approaches 0 of f of x plus h minus f of x all over h is equal to the derivative, the slope of a tangent line. So if we apply that definition here, we have the limit as h approaches 0 of f of x plus h. Well, this is a constant, so f of x plus h does not change it. It's still a constant minus the original function, which is that same constant over h. And we get 0 over h, which is equal to 0. Now you might be saying, well, I can't plug 0 in because I get 0 over 0. Well, remember, this is the limit as h approaches 0. So technically we can plug in a number that's just off of 0. And when I take 0 and divide by it, I will in fact get 0. So the derivative of any constant is 0. Now let's move on to something called the power rule. The power rule is for our problems in the form of the derivative of, let's say, x squared. Okay, so we're going to take a general function, derivative of x to the nth power, and we're going to try to figure out what that derivative is by using the limit definition. So the limit definition says the limit as h approaches 0 of x plus h to the n minus x to the n all over h. Now this is where this one gets a little bit hairy. X plus h to the n. Well, we know that starts with x to the n. We know it ends with h to the n. And we know we have to subtract x to the n. And that is all over h. So let's take a little sidebar here and let's discuss x plus h to the nth power. Well, let's say it's x plus h to the second power. That would be x squared plus 4xh. Oops, I'm sorry, 2xh plus h squared. And if I had made it the third power, x plus h to the third power, that would be x cubed plus 3x squared h plus 3xh squared plus h cubed. One thing to note is that the second term has a single h in it, and the other terms are increasing, h to the second, and then finally h to the third power. This starts as h to the first, increases to h to the second. Now if I go to the fifth power or the 10th power, the second term would have a single h, and then there'd be an h squared, h cubed, h to the fourth, all the way up to whatever that was. If it was the 10th power, the last term would be h to the 10th, and so on. So the important part to realize here is that we have plus some number. And in this case, notice the 2 and the 2, the 3 and the 3. So in this case, it's going to be n. N x to the n minus 1 times h to the first. Notice our degree of x dropped down from 3 to 2, from 2 to 1. A fourth degree would drop down to cubic, so on and so forth. Now it's irrelevant what this term here is, but I'm going to tell you it's n times n minus 1 over 2, and that'll be x to the n minus 2 and h squared plus dot dot dot. We continue till we get to h to the nth power. And really the significant part is to understand how the h's work. There's no h's in the first term. There's 1, and then there's 2, and then there's 3, 4, 5, up until there's n h's in the last term. The relevance of that, of course, comes into play here shortly. X to the n and negative x to the n cancel each other out, so they're gone. And you need to notice that every other term has an h in it, so I can factor that h out. This is left with n x to the n minus 1 plus, well, this had two h's, so it's still there. However, it's now h to the first. And then we'll have a bunch of stuff with h to the second, then a bunch of stuff h to the third, all the way down till we get to this last term, which had n h's, and it now has n minus 1 h's. The significance of that, remember, is, since we're following our notation, we have not taken the limit yet. We have not plugged 0 in for h, because frankly we can't. We have h in the denominator, but we no longer have h in the denominator. So I cross those guys out, and the beauty of this is what happens to all of these terms that have an h in them. They head to 0. All this stuff heads to 0 because h is involved, and when I plug a 0 in for h, they're gone. So I am left with n times x to the n minus 1. And that is my power rule shortcut for taking the derivative. Let's look at a couple examples here. Let's take, for instance, the derivative of x to the 5th power. Now, if we were doing the limit definition, that'd be extremely annoying because we need to do x plus h to the 5th. You know, that's a lot of tedious stuff there. Well, our new power rule says that I just take that exponent, drop it in front, I write my variable, and I decrease the exponent by 1 degree. 5 minus 1 is 4. And there is my derivative in terms of x for any point on the curve x to the 5th.